All right, good morning, pre-calculus, or actually Calc 2, sorry. So today we're going to talk a little bit about Taylor polynomials. Okay, and why we're going to do this. Okay, Taylor polynomials, this approximates other functions to a polynomial. So the idea here, nonlinear or non-polynomial functions, so approximates other functions to polynomials. And why do we want to do that? Well, and the reason we want to do that is because calculus with polynomials is pretty easy, and calculus with logs and e's and functions you don't know yet can be a little bit more difficult. Okay, and sometimes we can't actually integrate or take the well, we can usually take derivatives, but we can't usually integrate those polynomials or those functions without some really hefty approximations or some really hefty calculus. So what we do is we just approximate them as polynomials. And you can integrate polynomials because that was on your first quiz, and I know you guys can do that. So this gives you the tool to say, like, well, I didn't study those, but if we need an integral, we can approximate that. So the whole point of this is like we can kind of fudge around functions we may not know, or functions that we can get analytic form for them, but we may not be able to have a nice integration for them. A classic example is if you took statistics, right, 1 over square root of 2 pi, e to the negative x squared minus mu, so pi sigma squared, x minus mu, squared all over 2 sigma squared. Like if you took statistics, like that's the normal distribution, okay? And it's like, well, if I graph it, like you should be able to integrate that. Like, yeah, we have with the table, but it's your calculators. But it's not something that like I could just say, well, let's go ahead and integrate from negative infinity up to like 1 and just get an answer. Okay, because this function, even scaling it down difficulty wise, just doing this is not a function that we know how to integrate. Doesn't have a nice form for it. So there's a couple of tricks we can do to integrate this thing. Since we know what the graph should look like, we might be able to plug in some values and use Simpson's method. But sometimes we want to use a different method, and we use a Taylor polynomial because we might want several different values. Okay, so we're going to do that. Okay, so this is the reason for approximating functions as polynomials before we go further. Okay, and when we do our Taylor polynomial, technically we're doing Maclaurin series rather than Taylor polynomials. And Maclaurin said, well, we're just going to scale it at 0. So this is a Taylor polynomial specifically at 0. When we have Taylor, we can put another point in there, and instead of hitting it at 0, we could do like, well, what if we wanted to do at 1? Okay, and it's pretty simple. Well, I shouldn't say it's simple, but it's a pretty straightforward thing to do. So instead of using x, we're going to do Taylor polynomials at x. This is what Maclaurin would be, x minus 0. We just move it. So this would be x minus 1 at Taylor polynomial for 1. Okay. So what we're going to do is we're going to approximate this polynomial. We're going to approximate this function. Okay. And we have an a sub 0 plus a sub 1 x minus 0. Okay. Plus actually f prime at a at 0, x minus 0 plus f double prime of x minus 0 squared plus and etc. Okay, so the triple prime, so third derivative. So yeah, if you're looking at this like this is going to start getting tedious. Like, yeah, it is. Okay, x minus 0, 3. So we're taking derivatives of all these polynomials. Some things are going to start to stack up. So if I take the second derivative, first derivative of x, right, we'll just get 1. Second derivative for x squared, that's going to be 2 times 1. Okay. Third derivative, right, that's of x cubed. It's going to be 3 times 2 times 1. So we're going to keep stacking up these coefficients here. So we're going to divide by the coefficients in order to keep everything matched up. Okay. So what we're doing with Taylor is we're saying, well, let's match it on the first point. Let's match the first derivative of the function. Let's match the second derivative of the function. Let's match the third derivative of the function. Okay. And we're trying to match all of these things up, and hopefully it'll be close enough, and we'll match the at infinity with all of the values. We'll match everything up. So the function value and all the derivatives will be matched up. We're not doing infinite stuff though. Just going to do it to like 2 or 3 or 4 and call it a day. Okay, I think your book likes 4, so we'll keep doing with 4. Okay, so one of the most canonical ones to do is e to the x. Okay, so what we're going to do is we're going to say, well, what's the 0th derivative? 1. Okay, so this is f0. Okay, the first one, this is just going to be e to the x times, right, that's the slope, times the value here. We're going to have a polynomial, so x to the 1. And then f double prime, take the derivative of e to the x, it's e to the x. We have x squared, but we took some derivatives, so we're trying to match them. So we're going to divide by the 2 factorial here, 2 times 1. F triple prime, okay, e to the x, but times this polynomial we're trying to match, it's going to be x cubed divided by 3 factorial. Okay, f fourth derivative, okay, that's e to the x. All I do is keep taking derivatives of e to the x. That's why this is such a nice one to start off with. So this is x fourth over 4 times 3 times 1, because we needed to get rid of, we need to scale the derivative correctly here. Okay, because we're not really taking the derivative of this. We're taking the derivative like a polynomial that approximates this. So to get e to the x, that's going to be 1 plus 1 over 0 factorial, technically, plus x over 1 factorial, plus x squared over 2 factorial, plus x3 over 3 factorial, and dot, dot, dot. Okay, and I know the book is very good about showing you like, well, let's see what it looks like, and we will go ahead and do something like that. So I just wanted to say, well, we have y is equal to e to the x, okay, and then we can see what that looks like. And then we could also say, well, what about y is equal to 1? Okay, that's nice. It approximates it right here. They match. But we don't want just that to match. We want, we want the second derivative or the first derivative to match. So 1 plus x. So you can see the blue line and the red line, they kind of approximate each other. See, okay, well, what about the second derivative? Let's let that match. So x squared over 2. You can see, well, they're getting close, but it's way over here. It's like way off. So watch what happens when we do 3 plus x to the 3 over 3. I'm going to say factorial. 2 times 1 is the same as 2, so I don't really need a factorial here. If you want for completeness, we could always put it in, but it didn't change anything. And what we're trying to do is we're trying to match e to the x at 0. So this is going to have pretty good, excuse me, pretty good approximations near 0. And then as soon as you get away from 0, it's going to be less so, especially down here. Okay. And then we can just keep going. Okay. And yeah, at infinity, at the limit, okay, it does actually equal. Okay. But you can see, like, well, infinity better be an odd number, but at infinity, we don't really care. But we're just going to keep going and going and going until we've approximated this. So it will actually match up. Okay. And these are really useful in other classes because we usually expect you to know derivatives of e to the x. But in other classes, like, we don't always want to deal with, how to do this. And an example, you guys don't actually get to do all of this. The engineering kids learn a lot of other nonlinear functions. But like there's not a polynomial, like you can't do this. You can't set a polynomial equal to an exponent function or a polynomial equal to a logarithmic function, okay? Or minus 1 plus x or something. So when we're trying to figure out like, well, where do they meet? Like you can't do this. There's no analytic way to do that. As soon as you say, well, you know, how would I do like a 1 plus x squared minus x cubed is equal to ln x, ln 1 plus x. Like, how do you get rid of the natural log? Well, we raise both sides to the e power. So we have e 1 plus x squared minus x cubed is equal to 1 plus x. Like, great. How do I get rid of the e? Well, we take the natural log, and then we're back to here. And you never get any kind of analytic solution. But if I could approximate this guy with another polynomial, we'd have polynomial equals polynomial, and that is something we can actually solve for, okay? So a lot of times people want to, you know, this is the classic, like, where do these things meet, right? 2 to the x equals x squared. This is a very classic problem. There is no analytic solution to this because what's your first move? Oh, take the log of both sides. And now you're like, okay, I've got x, ln x is equal to ln x squared. Like, great. I'm back to where I started because I can't do this either. But if we could approximate this thing with Taylor polynomial, we know there's 3 solutions, so we do a Taylor polynomial up to 3, we'll be able to solve this thing. Okay, because so we just have a cubic equals a quadratic, and we can combine and solve. Okay, so that's the other reason we want to do this is like we have non-polynomial functions trying to equal polynomial functions. You can't solve them very well. So if we approximate the non-polynomial function with a polynomial, now we can solve. Okay, and then the other reason is like there are certain functions that we just simply can't integrate. So we approximate it with a polynomial. Now we can integrate the polynomial and then solve for that one. Okay, so those are the real powers for this, is doing approximations. There's a very famous problem for differential equations. Okay, we were trying to figure out like the pendulum. And when we go ahead and do this, like it's like a sine, okay? And the sine is a ratio, it's opposite of hypotenuse. But you know, we're talking about, we're measuring the vertical distance, something moves over a circle, and this is what we get as a curve. And you guys know, like, you've done some differential equations now, and non-polynomial differential equations, like with a logarithm, those are hard. So if we approximate with polynomial, we're going to be a lot better off. Okay, enough of me going on about how this works. So we'll do some examples, and I'll try to show you what's going on with this. Okay, so let's see here. Let's some homework. Okay, back one. All right, we'll take a similar question. All right, this will work. Okay, actually, I still want to do the 5 one because somebody asked about it. So if we do a polynomial, we have f of x equals, and this will be e to the negative 9x. Okay, and they want to say, well, we're going to approximate this to degree 4. Okay, so what I would do is I would make a little chart because these do get a little tedious. Okay, we're just going to go ahead and do that. So degree first. So what is my first derivative? F of 0, right? That's e to the negative 9x. Okay. F prime, right? That's going to be negative 9 e to the negative 9x. F double prime, that's going to be 81 positive e to the negative 9x. Okay. F triple prime. Okay, and I apologize if you do not know what 9 cubed is. Okay, so this is just going to be 9 raised to the 3rd power. Okay, 729 e to the, oops, this should be positive. I'm sorry. This one should be positive because we take the derivative, it's negative 9. This one will be negative because this will come down to be negative. And then finally, thankfully, F4, okay, That's going to be times another 9. Okay, 65, 61, but it's going to be positive 65, 61 e to the negative 9x. Because I'm going to bring down the negative 9, it's going to multiply, it's going to be positive, and that's where we are. Okay, so those are all my derivatives. Delightful, I know. Okay, so, and there we go. I said, well, we are interested at 0. Okay, so we're interested at x equals 0. Let's plug in 0 in for x. So this is going to be 1, right? E to the 0 is 1. This is just going to be negative 9. So e to the 9 is, e to the 0 is 1. This is going to be 81. This is going to be negative 729. This is going to be 65, 61. Okay. So that's my, all I did was plug in 0 into my x's. Okay, every time. In this case, this is why we always do e to the x first, just because it's really nice and easy. These are all going to be 1s, so we're all set. Okay, so these are the values of my e to the x. So when I'm plugging this in, right, we're going to get one no polynomial, okay, just 1. And this is going to be f to the f of 0, okay, over 1 factorial plus, and this is going to go with x f prime of 0 over 1 factorial. This is technically 0 factorial, sorry about that, plus x squared over 2 factorial times f double prime 0. Okay, so that's why we generated all the double primes and everything like that. All right, so well, we're going to go ahead and generate our polynomial, right? This is going to be 1, right, times this guy. So here's this 1, okay, over 0 factorial plus x over 1 factorial. Okay? And then we're going to plug in, like, well, what's f prime of, right? What's f prime of x at 0? This was negative 9 because we're matching up the slopes. Okay, and then plus we have x squared over 2 factorial times, right? This was f prime of 0. This is going to be f double prime at 0. So f double prime at 0 was 81. We are matching up, right, the second derivatives here. Matching up the third derivative, so this is going to be plus x cubed over 3 factorial, okay? And then f cubed, triple prime here, that's going to be negative 729, okay? And then finally, plus x to the 4th over 4 factorial, and then we have 65, 61, okay? So just to write that down as like one line, the Taylor 4 polynomial, this is going to be 1 minus 9x plus 81 over 2 x squared minus 729 over 3 factorial x cubed plus, and then we're going to have this guy here, and this is going to be 65, 61 over 4 factorial x to the 4th. Okay, so that's our Taylor polynomial. We can check. Okay, I always find this to be kind of neat thing because looking at it from Desmos is kind of a cool idea. Okay, we have y equals e to the negative 9x. Okay, so we're gonna have to kind of delve really close in here. Okay, because it's pretty steep sloped. Okay, so let's go ahead and take a look. It's going to be 1. Oh, sorry. Y equals 1. Okay, minus 9x. Okay, and you can zoom in and kind of see, like, yeah, we're kind of approximating that. Plus 81 over 2, 2, and then x squared. Okay, again, we're kind of approximating it. And you don't have to do this forever. You don't have to do this for any of them, really. I just think it's kind of neat to watch, like, the polynomial, the Taylor polynomial kind of hug the actual function. I just think that's kind of neat. So sorry. Those were this one time. We won't do it again. Okay, divided by 3 factorial. Okay, and that's x to the third. Okay, so we're still approximating that. Okay, and then finally plus what was it, 65, 61 over 4 factorial x to the fourth. Okay, so it just kind of gets closer and closer and closer. And notice this one, because it's negative, approximated the negative side a lot better than the positive side. That's because we're pretty much looking for either negative x, which is going to have this minus plus kind of thing here. This should have been minus plus. Yeah. So that's what we're doing with that. Okay. And you might find like, well, the numbers are ugly, but integrating this would be a lot easier, okay, than some of the other functions we've dealt with. Okay. So that's what we have. All right. So let's see here. We want, okay. So what we have written down for our Taylor polynomial here, we have 1 minus 9x plus 81 over 2 x squared plus, what was it, 729? Let's see, over 3 factorial, that would be 6. Okay, and it was x cubed. Oops, that should have been a minus, right? Yep, that should have been a minus. Right? And if finally at the end, that was, I'll check my coefficient here. That's 65, 61. 65, 61 divided by 4 factorial. Okay, x to the 4th power. That should be our approximation. Okay, provided I typed everything incorrectly. Check. Okay, so that's kind of what you're doing with this, and then they just give you a bunch of practice problems to work with. These tend to be a little bit more tedious. Okay, and we'll go ahead and do that. Don't forget your chain rules when you're doing this. In this case, we don't have a chain rule, but don't forget to do the chain rule. That's the biggest mistake people make. Okay. They do this in engineering class too, because that's an important skill for everybody to have, just be able to approximate this. Okay. Because again, there are certain functions you simply cannot integrate. You can type that into Google and say functions that have no integral. There'll be a bunch of functions that you don't really know. Like that one does not have an integral. Okay, it's like I can do derivative. Like, yeah, you can, but you can't undo it. Okay, so we approximate this with a polynomial function, and then we integrate if we have to get an answer. Okay, so here we go. Let's go ahead and write down the function that we have. Okay, this is f of x is equal to, okay, and this is 3, I'm going to write it like a calculus problem, 16 plus x raised to the 1/4 power. Okay, that's what we have. That's what they meant. So we go ahead and we write that down. So our 0th derivative, right, that's going to be 3, 16 plus x raised to the 1/4. Our first derivative, that's going to be 3 times 1/4, 16 plus x, right? We go ahead, what is 1/4 minus 4/4? That's going to be 3/4. Okay, negative. Okay, and there's my coefficient from the 1/4 that came down in front. Okay, f double prime, that's going to be 3 times 1/4 times negative 3 times 1/4. Okay, so this is going to come down in front. 16 plus x, and then subtract 1, so that's going to be minus 7, right, over 4. Okay, that's our second derivative. F triple prime. Okay, and I would just caution you, like don't do too much in one step because it's so easy to mess up. Okay, especially if you have a chain rule in here. Okay, 4 more, that's going to be minus 11 over 4. Okay, And then finally, our fourth derivative, okay, that's going to be 3 times 1/4 times -3/4 times -7/4 times -11/4, okay, times 16 plus x raised to the, right, 1/4, so that's -15/4. Okay, and now we'll go ahead and simplify this down a little bit. Let's see here. We have 1, 2, 3, 4 of these. Okay, double. Okay, so first derivative is this one, second derivative, third derivative, and then finally fourth derivative. So 1, 2, 3, 4. Okay, so this is 4 to the fourth. Okay, and here we have 1 times 3 times 7 times 11. Yeah, best of luck with that. Okay, sometimes you can go ahead and make a nice little pattern out of this. I don't know if I would bother trying to do that for you guys. So 1 times 3 times, so we have 3 times 7 times 1. Okay, times 11. Okay, and then this was times the first 3. Okay, and this was 693. That's this first stuff written up. And we have 16 plus x raised to the -15/4. Okay, so that's what we have for that. This is 4 cubed. Right, this is going to be 1, 2, 3. That's going to be 64. Okay, and then we have 1 times 3 times 7. Okay, and then times the 3 at the beginning. That's 63. Okay, we have 16 plus x. Dang it. Negative 11/4. Okay, and all we're doing is we're just doing this more and more and more. So this is going to be 9/16, right? 4 times 4, and then we have 16 plus x to the -7/4. And then this is just 3/16, 3/4 rather, 3/4. Okay, and then we have 16 plus x raised to the -3/4. And then it's just, right, 3/16 plus x to the 1/4. All right, now we also have to type in, like, well, what happens when we go ahead and plug in x equals 0? We're going to have to get all of these numbers too. Okay, so we're not done yet. Just calculate it out the coefficients to make it a little bit easier. But then we're going to go ahead and plug in the x equals 0 and then plug in all these numbers. Did it tell us what to do with the values there? No, it did not. Okay, so yeah, we're just going to have like 16 raised to the 1/4 power here. Okay, or the 7th power, 7/4 power kind of a thing. Okay, so let's see here. Again, let's see if we can't. Okay, so my Taylor polynomial, right? So this is f of 0. Right, so this is, what is my value for f of 0? We're just going to have 3 times 16 to the 1/4 power. So this is 3 times 16 to the 1/4 power. Okay, no polynomial, no x's. We're just matching the polynomial. So this is my constant term. Okay, and then we're going to have plus f prime. Okay, and then let's go ahead and go with that. But it's going to be 3/4. 16 to the -3/4 power. Actually, I should realize that 2 to the 4th is 16, and then that's a lot easier, right? Because 16 to the 1/4 power is just 2. Okay, so we could probably do something like that. Okay, let me go ahead and deal with this before we go too much further. Okay, so this is just going to be 3 times 2. Okay, so this is going to be 3/4 times, we have 16 to the 1/4 power. So that's 16 to the 1/4 raised to the -3. So that's going to be 3/4, okay, times 2 raised to the -3 power. So that's 1/8. So we have 3 over 4 times 1 over 8. So that's going to be 3 over 32 x. All right. So it's a positive number. So yeah. And then f double prime. Okay, that was, what was that going to be? That was going to be 9/16. Then we have 16 to the 1/4, which is 2, raised to the -7, the board. Okay, so this is going to be 9 over 16 times 1 over 2 raised to the -7, raised to the 7th, because that's, the 2 came down here, so that's positive now. And it's the second time this came up this week. I know 2 to the 5th is 32, 2 to the 6th is 64, 2 to the 7th, double it is 128. So this is 9 over 16 times 1 over 28, 28. And I'm not going to bother trying to sort that out. We're just going to use calculator. So 16 times 128. So this is 2040. So this is 9 over 2048 x squared. Oh, divided by 2 factorial. So this is going to be 496, 498 rather, times 2. Okay, that's 496. So that's going to be 9 over 496 x squared. This one's negative though, isn't this? Okay. Yeah, because this one came down in front. So this was actually going to be a negative when I came over here. Okay. So you can see, like, there's a lot of bookkeeping, there's a lot of keeping coefficients straight and everything like that. So having a nice little system, tables work really well. I would say that's probably the best bet you're going to have with this. Okay, so this is 63 over 64. So this is a positive. All right, and then we have 16 plus 0, which is 16, raised to the -11/4. Times x cubed over 3 factorial, right? I put the factorial in. No, that's just this. All right. So that's this one. Okay, 2 negatives, we made a positive. Okay. So that's going to be 63. This is going to be 63 over 64. If I plug in the value here, we're going to have 1/2, right? Because that's 16 to the 1/4 power, raised to the 11th, okay? Times 1 over 3 times 2 times 1 is 1/6, x cubed equals, and that's what we're going to be dealing with, okay? So what do we have? We have 64 times 2 to the 11th. Oh, these are going to be delightful. Times 6. Okay. So we're going to have 63 over 78,632 x cubed. Okay. Oh, I'm regretting this problem more and more. All right. So let's see. My last one here. Okay. For the 4th power. Okay. So it's going to be minus. Right, because that's what we have is the minus in here. So it's going to be 693 4 to the 4th. So there's going to be 693 4 to the 4th power. Okay, that's 256 times, what do we have here? We have to the 4th power, so that's 652, 2 to the 15th, so it's 1/2 raised to the 15th power times x to the 4th over 4 factorial. So there's going to be 693 over 256 times 2 to the 15th times 4 factorial, and we'll see what we get. Okay, so this is going to be 256 times 2 to the 15th. Okay, this is all in the denominator, so I don't have to worry too much about that. Okay, times 24, that's 4 times 3 times 2 times 1. There we go. So that's a little number there. So that's 693 over 20132 6592 x to the 4th. Okay, and we would type that into the homework here. Hopefully we got all the digits right, and then move on. Okay, let's see what the rest of the problems look like here. Okay, x equals 0, that's fine. Logarithms are a little bit better. Don't forget your chain rule. Okay, don't forget your chain rule when you're doing this. So just to, I'll start another video to do this one because I think this one has gone long. Okay, I might just do like one video per problem kind of a thing. Notice they're all at 0 so far. So we're just doing Maclaurin series. Honestly, with 4 to approximate, so we're going to plug in 1.004 when we get there. Okay, it's close enough to 1. Oh, yeah. Okay, we'll do this one. Oh, type this in. Okay, so they give us this. So we just type in 1.004 here. Okay, and we'll just keep going with that. Polynomial degree 3, where they give us all the derivatives. Thank you very much. I think. Okay. All right. So not too bad. We don't have to generate anything that starts off with a weird spot. So I'll stop there. That way the video has been too long, and we'll see you in the next video. All right. Thank you for the question. Bye-bye.